Hi, and welcome to the Origins Podcast. I'm your host, Lawrence Krauss. I'd like to begin here a new segment, a new series, if you wish, for the Origins Podcast, which will be a series of mini lectures on physics, from the most simple aspects of physics to the most advanced. Consider it a mini course on physics if you want. And over the next period of months or year, I'll be developing a variety of lectures that hopefully will give you insights into how physicists think about the world in ways that you might not have gotten before. So let's begin with Lecture 1, which is a tour of the universe. Seems a good way to start. Now, I want to introduce you to the kind of tools that physicists use to describe the universe, which after all has many, many different scales of space and time. And then we'll go over exactly what those scales are for the universe. Now, the problem at the very beginning is because there's so many different scales, we can't use the kind of mathematics, the kind of descriptions, even verbal descriptions that you're used to in everyday experience. Consider, for example, the Earth and the Sun here. In units that I would like to use, 10 light minutes, it takes about 8 or 9 minutes for light to get from the Sun to the Earth. And so that's a nice unit to describe distance when you talk about cosmic scales. Well, that's fine. That's if I represent that distance there between the Sun and the Earth by this kind of scale. In a linear scale, if I wanted to talk about the distance between the Sun and its nearest neighbor, the star next closest to the Sun, then in order to do that in a linear scale, I'd have to separate those by about 3 miles. So clearly, I don't have a board or a projector that's large enough for that. And obviously, that's just the nearest star. If I wanted to go beyond that, I have to consider even larger scales, larger blackboards, if you want. So we have developed a tool, a mathematical tool, which is quite simple, which many of you may be familiar with, which is called powers of 10. We talk about units in science in terms of powers of 10, and there's a bunch of reasons for that I want to introduce you to. In the first case, it allows us to simplify our descriptions and allow us to talk about many different scales at the same time. Here's a linear scale of going from 0 up to 160 and beyond, where every line is 10 units. And okay, well, that allows me to get some numbers there, but a simpler way to do it is to consider taking the digits from 0 to 10. I've got them here. And calling 10 and 0 by their powers of 10 value. So we call 1 10 to the 0 and 10 10 to the 1. 1 power of 10. Okay, in that scale then, 100 becomes 10 squared, and 1,000, which you can't even see on this scale, is now just the next unit up, 10 cubed, and we could go to 10,000, which was just 10 to the 4th. And you can see that on this scale, I can describe vastly different sizes, magnitudes of numbers in a way that at least is on a single frame. But you just have to remember, and this is the important thing, that each tick is a factor of 10 bigger than the tick before it. Now that's for large numbers. For small numbers, we can do something similar. Say, take the numbers from 0.1 to 1, as you can see on this linear scale here, and consider 0.1 to be 10 to the minus 1, 1 over 10. And then 0.01, which we could, again, if we expand on a linear scale, that this single space there into 10 separate units, 0.01 becomes 10 to the minus 2, and so on and so on. This allows us to talk about scales from the very large to the very small in a single graph. It's more than just useful pedagogically from the point of view of presentation. You'll see it's incredibly important for actually understanding the details of how physical systems work. And we'll talk about that in the next lecture. But I want to use this scale here to try and discuss the physical universe. And in fact, because we're talking about powers of 10, I want to show you the physical universe on scales of meters. And I have down here 10 to the minus 28 meters, all the way up to 10 to the 28 meters, with 1 meter right in the center. Okay? And I want to talk about what we know about the universe on scales not quite this large, but as large as we've ever been able to see, and as small as we've been able to see. And that gives us a sense of the universe as we know it, the playing field physics, if you will. So I want to borrow here very famous photographs from a series of books that were first developed by Charles and Ray Eames, graphic designers, called Powers of 10. And it gives you a sense of these scales. And I update it periodically to show some more recent images. But it begins with a man sleeping in a park in Chicago. The scale of this is 1 meter across, 1 meter horizontally and 1 meter vertically. This is a very familiar scale. It's a scale of human beings. By the way, it is kind of fascinating, and students have asked me, is it a coincidence that human scales happen to be somewhere in the middle of this range of observations we've made? Well, I think it's kind of reasonable to expect that we would try and look up and at as large scales and as small scales as we can. Perhaps not too surprising that we're somewhere in the middle, and maybe it's just a myopic view of the universe. And if we had a different scale, the centerpiece would be a different number. But for us, 1 meter characterizes a human scale of the man and the clocks and his food and everything else sleeping in the park in Chicago. Now, each click in this set of images is going to take you a factor of 10 bigger. So that was 10 to the 0 meters. 10 to the 1 meters is now this distance across. Now you can see this man sleeping in the park in Chicago, and you can begin to see that he's in a park. It's still a very human, familiar scale. When we go up to 10 to the 2 meters, well, we can still see the man sleeping in the park. We see the highway nearby. This is still a human scale, but 100 meters is about the size of, a little larger than the largest animals ever made. So when you consider biology, the largest animals that ever roamed the earth would have certainly fallen within this picture. And it turns out, by the way, if you put human beings evenly spaced over the entire earth, everyone would have a space about 6 times larger than this area you can now see. If we spread the 7 billion or so people on Earth in uniformly that way. Well, we go up to the next scale, which is 1,000 meters or a kilometer, and you can of course see the structures. You can see a Wrigley Field, I think it is, and I think it's Wrigley. Maybe it isn't Wrigley Field, but it's some stadium. No, that's actually a football stadium, and I don't know the football stadium's name in Chicago. But you can see the scale of human architecture certainly encompasses this scale at its largest scale, less than a kilometer. Still familiar, and this would be the standard area where early hominids would roam, perhaps on within a daily basis, maybe somewhat larger. If we go up to the next power of 10 kilometers, well, you can see already the outlines of the grid of the streets in Chicago. Any evidence of the man himself is gone, but certainly evidence of human habitation is still here. 10 kilometers is an interesting scale because, again, for many people around the world, 10 kilometers represents basically the distance that covers almost all the time that they spend in their life, roaming over a scale of 10 kilometers or less. And that's 10 to the 4th meters. It's a scale of a reasonable size, center of a reasonable size, large human city, Chicago in this case, but it could be any other city. 4 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. We get to 10 to the 5 meters, and you can now see the entire metropolitan area. That's 100 kilometers. That certainly encompasses the size of most of the largest cities in the United States and other places around the world. If you were looking at this, if you could actually see the camera taking this picture, you could barely make it out if you were on the ground. It would be that high up in order to be able to take this picture. But you can now definitely see the lattice of lines. You can definitely see still clear evidence of human habitation, human civilization. If you go up to the next scale, 1,000,000 meters, 1,000 kilometers, well, on this scale, the evidence of individual human habitation is gone. The evidence that humans live here is still there, but you can now see Lake Michigan, and you can begin to see the weather, and the camera now would be so high up that you definitely couldn't be seen, but you also couldn't see any evidence of individual human beings already at 1,000,000 meters. Okay. Now, a factor of 10 beyond that is quite a jump, because you now take us to almost the size of the Earth, 10,000 kilometers. This is taken from space. This is an image, of course, of you can see Chicago in this picture. You can see the large-scale weather patterns. It's kind of interesting to realize that for humans who already had begun to map the Earth, map the parts of the Earth they knew thousands of years ago, and eventually several hundred years ago had mapped the entire Earth, this image of what the Earth must look like from space was hypothetical. It wasn't until 1967 or so that we had satellites that could go up and take this picture. So it's only been in the last 60 years or so that humans could actually take a selfie of the world and see what it looks like. Now it's fairly common. Of course, you can look at it online on the internet, and the space station, which goes around the Earth every 90 minutes or so, sees these kind of images all the time. We're now at 7 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. Another factor of 10 to 100,000 kilometers, and you can now begin to see the Earth isolated. And this is an artist's rendering against a background of stars in our galaxy. Of course, from here, it's not so clear that you can tell that there's any humans. If you just look at this image, that any humans are occupying the Earth, or in any case, any life forms. Of course, if you look at colors and spectra, that's a very different thing. And as we look to try and find potential habitable planets, we'll be using all of our tools to try and look for indirect evidence of life. Now, if you can barely see life directly here on Earth, so close to it, you can imagine how much harder it is to infer the existence of life on distant exoplanets around other stars, part of the challenge. This is 100,000 kilometers, not quite the distance to the moon. Not quite the distance to the moon, but now if we go by a factor of 10, here you can see drawn is the orbit of the moon. This is the largest distance that individual humans have ever traveled out to the moon back in the days of Apollo. And we sent, of course, instruments to look at the moon and land on the moon, but human beings have never traveled further than this directly. We've sent our technology out much farther, but this is the full range of human travel over human history. And we hope in the next decade to be sending humans back to the moon and potentially create a permanent base on the moon. And all of that's going on right now. We're sending rovers to the moon now to explore evidence for water, which might help us understand not just what natural resources we have to provide for potential astronauts and housing on the moon as we learn how to build facilities there, but the moon, of course, would be a great launching pad for rockets to go elsewhere in the solar system, because the gravity of the moon is so much smaller than that of the Earth, because the moon is much lighter. It takes less fuel to escape the moon's gravitational pull. And so it's quite possible over time in the future, we may use the moon as a kind of refilling station, a kind of new launch pad, as well as other scientific activities that will take place on the moon. This is now 10 to the 9th meters, and it's 1,000,000 kilometers or 1 billion meters, 9 orders of magnitude larger than the scale of the man sleeping in the park of Chicago. When we go up by a factor of 10 again, you can still see the moon's orbit in this slice. This slice is basically the distance that the Earth and the moon, of course, going around it, covers in the Earth's orbit around the sun in 4 days. 4 days, this happens to be in October. So the Earth, of course, takes 365 days to go around the sun, and in 4 days it encompasses this distance. You can see in 4 days the Earth is moving over a scale much larger than the entire distance between the Earth and the moon, and of course the moon is being dragged along with the Earth. Another factor of 10, and you can begin to see the orbits of 3 of the inner planets. We can see the Earth's arc as it encompasses about 6 weeks of travel at 100 million kilometers, and you can see Venus, and out there you can begin to see the orbit of Mars. We're beginning to see the inner planets of the solar system. When we go out by another factor of 10, 1,000,000,000 kilometers, 10 to the 12th meters, or about 7 times the distance between the Earth and the Sun, you can see now the orbits of all of the inner planets and the orbit of Jupiter. Again, this is an artist's rendering. And between the inner planets, between Mars and Jupiter, that area is also populated by lots of small objects, asteroids and meteors in this belt between Mars and Jupiter, some of which eventually get kicked out. And you can see if you look at the moon, you can see the craters on the moon or craters on the Earth. Some of them impact on the Earth. And of course, in the early history of the Earth, they were quite important, probably for delivering water to this planet. But now at 1,000,000,000 kilometers, this is the inner part of the solar system, 10 to the 12th meters, 12 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. Next scale, 10 billion kilometers, you can begin to see all the paths of not just the inner planets, but all the outer planets. And just to show how science changes, when this image was first made by the people, Charles and Ray Eames and those who followed it, the outer sort of skewed orbit is the orbit of Pluto, because at that time Pluto was considered a planet. For me, it always still will be. It turns out the orbits of the other planets are pretty much in a plane, whereas the orbit of Pluto is off kilter. Another reason perhaps to consider it not as a planet, but here it is. And we've now sent human spacecraft well beyond this region. We've, of course, sent the Voyager spacecraft well beyond the outer limits of the visible part of our solar system here. And then recently, a few years ago, we had the New Horizons spacecraft, which went out past Pluto and took pictures of that and other what are called Kuiper Belt objects. This is roughly the largest scale that human technological activity has taken place over directly. We've sent objects out to this scale of 10 billion kilometers, or 10 to the 13th meters, 13 orders of magnitude larger than the scale of the man sleeping in the park of Chicago. Out at this scale, by the way, on the way out, as we sent objects, this is a picture from the Cassini spacecraft, which went around Saturn and has explored Saturn and its moons. The interesting thing that I always love about this image is if you look at this spot here, which you probably can't see with the camera there, but you can go online, you can see a small dot. It's a pale blue dot, and that, of course, is the Earth as seen through the rings of Saturn. By the time we're out at Saturn, the Earth is just a speck in the sky at best, and once you're well past Saturn, the Earth is not visible to the naked eye if you had a naked eye out there at all, giving you a sense of our fragility and perhaps our cosmic insignificance. Okay, by the way, all of these objects, it turns out, circulate counterclockwise around the sun, indicating that at some point there was a gas cloud that was circulating and orbiting the sun as it began to collapse around the sun, fragmenting into the planets we now see today. When you're out at 100 billion kilometers, the sun is still by far the largest, at 10 to the 14th meters, by far the brightest object in the dark sky. You can sort of already, if you could, see the planets orbiting their kind of Copernican orbit around the sun. It's obvious that this is the solar system, our small home, which until relatively recently in human history is all we knew about in terms of the direct universe. We'd see the stars in the sky, but this was our home, and the discovery of planets around our sun, our solar system, was our local neighborhood, and it still is our local neighborhood. We've now, of course, discovered there are solar systems around almost every star, solar systems that are strange by comparison. We used to think that perhaps maybe we're strange by comparison. We used to think that our solar system was typical, but we've learned that the nature of planets orbiting stars varies more than you could have possibly imagined before. At 14 orders of magnitude larger than the scale of the man sleeping in the park in Chicago, our home. When we go to the next scale, at best you can see the star standing out, the sun standing out against a background of other stars. It's the closest star in the region, and any real evidence to the naked eye of all the planets around our sun, much less the Earth, has disappeared. "16 orders of magnitude, 10 trillion kilometers." This is a scale that's a particularly important scale. It's 1 light year. It takes light about a year it would take a light beam about a year to travel from one end of this image to the other. And this is at 1 light year, we still haven't gone out to the nearest star beyond our sun. That's why our sun is still the closest object in this frame. It stands out against the background stars. But by the time we go out to 10 light years, or 10 to the 17th meters, 10 trillion meters, then you, 10, actually more than 10 trillion meters, 10 to the 17th meters, we have 10 light years. We call that 3 parsecs. And that's a unit that, a parsec is roughly the distance between the Earth and its nearest star other than the sun. And you can begin to see at this point, when you're out at 10 light years, there are other stars closer to us in this image than the sun, and the sun has disappeared into the background of stars. It's nothing special. By the time we're 17 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. 100 light years, now distant stars. You can see one bright star there. It's called Arcturus. It's prominent in the northern sky of Earth. It shines brightly. It's intrinsically far more luminous than the sun. The sun is a medium-sized star. There are stars that are much more luminous than the sun, and of course there are a lot of stars that are much less luminous than the sun. Again, it's a strange fact that our sun seems about average. Is that important? Is that significant that we evolved around an average-sized star? Does that mean life can only do that? Or could there be lots of life around the many, 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 many smaller stars than the sun? Well, that's important because most of the planets that we've seen outside of our sun orbit much smaller stars than the sun and much closer than the orbit of, say, even Mercury. And are any of those planets habitable? Do they have liquid water? These are the kind of questions that we're trying to answer. And ultimately, of course, to look for some evidence of life in the universe other than the life on Earth. We're now at 1,000 light years away. 1,000 years, we're beginning to see the kind of scale of our galaxy. It's 1,000 light years is larger than the width of our galaxy, or the height of our galaxy, I should say. From one end to the other, you'll see our galaxy. It's kind of flat like a pancake, but the width of that pancake that is less than about 1,000 light years. But you can begin to see that the stars are not uniformly distributed, and by the time we go out to 10,000 light years, you can begin to see the structure, the filamentary structure, which will eventually become the spiral arms of our galaxy. And our sun is on one of the edge of one of those arms. I should say, by the way, that within this scale, and the one we saw before, 1,000 light years, basically almost all the stars in the night sky that were known to humans existed in a scale smaller than 1,000 light years away from us. The galaxy itself is much larger. This is 10,000 light years, 10 to the 20th meters. To get to the scale of our galaxy, we have to go to about 100,000 light years. Our galaxy is about 100,000 light years across, 10 to the 21 meters. And you could see, if you were standing outside of our galaxy, the filamentary structure and the fact that our sun is on the edge of one of the spiral arms. And again, is that significant that we're on the edge of the spiral arms? Is that important for the evolution of life? We don't know. Here is not our galaxy, but one of the nearest galaxies to us, and you can see a spiral galaxy. In fact, we knew we lived in a spiral galaxy, which is flat like a pancake, but it was just, we knew that from indirect inferences of counting stars and looking at the dynamics and understanding the dynamics of our galaxy. But it wasn't until about 1990 or so, when we set out the COBE, Cosmic Background Explorer satellite, which was designed to look for the cosmic background, but it could also look at microwave radiation from our galaxy. Most of our galaxy is obscured by dust in the visible region. Well, microwaves, you could actually see more of the galaxy. And I remember when this image first came out in about 1990. This is our galaxy as seen from our location of the edge. And you can see, once again, it is a spiral galaxy. We're at the far outer part of it. This is looking in, and this is the luminous stars as seen in the microwave, shown here in, of course, false colors. So proving that our galaxy is, again, about a spiral galaxy. And the width of the galaxy here is less than 1,000 light years across, and across in that direction about 100,000 light years across. A typical large galaxy, our Milky Way galaxy, one of many, which we're going to see again. In the center of our galaxy, and this is an amazingly amplified image of the very center of our galaxy, taken by astronomers who were looking at this for over several decades, looking ultimately at and there's some films you can see of stars orbiting nothing that you can see. And it's been inferred that the center of our galaxy, there's a large black hole of about 10 million solar masses. And the astronomers who spent decades observing the motion of the planet, of those stars around that central black hole, proving, if you wish, that they were orbiting something that we don't see that looks and acts very much like a black hole. These observations were so difficult that ultimately these observations were awarded the Nobel Prize for being able to see, and indirectly, the black hole at the center of our galaxy. Now, using techniques that have allowed us to get a visual image of a black hole at a distant galaxy are being used to try and get a visual image of the black hole at the center of our galaxy, which would be quite fascinating. But to come back to our galaxy, that's about 100,000 light years across. When we go a factor 10 more, 1,000,000 light years, we still have our galaxy. You can see our galaxy and two small satellite galaxies, the large and the small Magellanic Clouds, which are visible from the southern hemisphere in particular. And those are sort of dwarf minor galaxies that are orbiting our own, maybe gobbled up. And until recently, those were the only two satellites we could see. But now we actually have seen that there are flows and many other small satellite galaxies that have been cannibalized in the evolution of the Milky Way galaxy. These are our nearest neighbors, if you want to call it that. They're not full galaxies. They're about 100,000 stars in them. And most galaxies are, our galaxy size are smaller, and the smallest galaxies we've seen are about the scale of the Magellanic Clouds. This is still smaller than the scale of the distance between us and the nearest galaxy. The nearest galaxy to our own, the Andromeda galaxy, which looks a lot like our own, is 2 million light years away, twice this distance. This is 10 to the 22 meters, 22 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. When you have 10 million light years, or 3 megaparsecs, 10 to the 23 meters, you're beginning to see other galaxies. Our local group of galaxies, we're a part of a local group of galaxies. And when you go a factor of 10 larger still, to 100 million light years, you begin to see that that galaxies themselves are clustered. And we're part of, on the edge of something that's called the Virgo cluster of galaxies. We're part of a large gravitational system that is bound. And these clusters, or superclusters, are the largest bound objects in the universe, containing tens or hundreds or in some cases perhaps up to 1,000 galaxies. These are the largest objects not only exist in the universe today that are gravitationally bound, but because of the dynamics of the universe and its expansion, they're the largest objects that will ever exist. No larger scale objects will be gravitationally bound ever in the future history of the universe if it continues to expand as it's expanding now. We're now at 100 million light years across, 24 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. And on 1 billion light years, you can again see this cluster here. And if you go out to the largest scales, we can kind of imagine, well, this is an old picture now. This is from the Hubble Space Telescope. We have new versions of this with the James Webb Space Telescope. Every image in this picture, except for that one, which is clearly a star, is a galaxy. We now know there are over 100 billion galaxies in our universe, and each galaxy contains on average 100 billion stars. And their distribution is important because it tells us about the primordial conditions that eventually led to the universe as we know it, because gravity is universally attractive. And if we look back in time, we can begin to see how these structures form and compare it to our theoretical calculations. And those things have revealed that our current picture of the universe, dominated not by the stuff you can see, by stuff you can't see is significant. These galaxies wouldn't have formed if they weren't themselves in a sea of dark matter, something that doesn't shine, made potentially of new elementary particles that we're looking for, in fact, on Earth, because these objects, if they're a gas of new elementary particles, they're not just out here, they're in this room going right through us now, and experiments are being done here on Earth to try and look for those things. They are relevant for trying to understand the structure that we see in the universe today. And it turns out all of this is embedded in empty space, and the energy of empty space dominates compared to the energy of everything you can see in this image. If we go a factor of 10 larger, you can begin, and this is obviously an artist's rendering of the fact that galaxies, not only are they clustered, they seem to exist on large kind of sponge-like distribution, sheets and filaments. That was very strange when it was first seen, but now by doing simulations, numerical simulations of how visible matter would collapse in a sea of dark matter, these filaments are exactly what you'd expect to see. They're the bright objects that trace the distribution of dark matter underlying underneath. Now, I want to show you a movie that was taken some time ago, that was put together some time ago. This is using one of the largest surveys of galaxies that was in the last sort of 30 years that's been taken. And you can see, of course, there's selection effects because these were only done on individual slices. You can begin to see these are the real filaments of galaxies. This scale is hundreds of millions of light years across. And you can begin to see that as we look out, and this will turn around in a second so you can see the three-dimensional structure of it. You can see that the galaxies are indeed located on these kind of filaments that help us understand the origin of structure since the Big Bang. This is the largest scale in which we can see matter, but if we go out to ever larger scales, more than 10 billion light years across, the largest distance we can see in the universe is, in fact, comes from the cosmic microwave background. If we're at the center, we can never see beyond a sphere located on this scale. It doesn't mean that there's nothing out here, but this is the largest scale we can see because as we look out, we're looking back in time. And for a time earlier than this, the universe was opaque. It was so hot at 3,000 degrees that matter became ionized, and we can't see radiation permeating that hot plasma beyond that. So this cosmic microwave background radiation comes to us from a sphere located that was basically when the universe was about 300,000 years old. Once it cooled down, then matter became neutral, and the light could propagate to us. This is the largest scale, therefore, that we can see in the universe today. About 26 orders of magnitude larger than the scale of the man sleeping in the park in Chicago. Now, I want to go back. With each click, I'm going 10 times closer to the Earth than I was before. And with 24 clicks, we'll get from the largest scale of the universe back to our familiar surrounds of the solar system, and the Earth and the moon, and the Earth itself, and Chicago, and the city, and slowly the human structures, and the man sleeping in the park in Chicago. Just 26 clicks of my clicker here took us from, in powers of 10, from this scale to the largest scales we can directly see in the universe today, in which we can experiment as we try and understand the origin of our universe and its potential future. Well, that's looking outward. As we look inward, we discover another fascinating micro-universe. With each click now, I'm going to go 90% of the distance down to the smallest scales we're going to see. So we go down and click, and of course this is still recognizable. You can see the skin of the man sleeping in the park in Chicago. At 1 centimeter, 10 to the minus 2 meters, you can already begin to see the folds in the skin, which are the creases are just a sign and the means of the skin's flexibility. If it didn't have these folds, you wouldn't be able to move around like this. Your skin can stretch and expand and contract. This is perhaps the last scale where things might begin to look familiar, because as we go in by another factor of 10 to a millimeter, we're going to begin to see the world as microscopists might see it. And we're going to end up within a cell passing along a tiny blood vessel just below the skin of the man sleeping in the park in Chicago. So if we go a factor of 10 more to a tenth of a millimeter, 100 microns, a micron is a millionth of a meter, you're beginning to see new details. And as we go a factor of 10 further, we can begin to see, in this case, a white blood cell in the blood of the man, just underneath the skin of the man sleeping in the park in Chicago. White blood cells are much larger than the red blood cells. Blood cells gives the blood its color. White blood cells are used to combat disease and the body's defense against infection. If we go inside of that cell, a factor of 10, 1 micron, a millionth of a meter inside the cell, we're beginning to get inside the protective membrane of the cell, and we're going to get closer to the nucleus of the cell. The nucleus of the cell is the powerhouse of the cell in many ways, and it contains something that's very vital. If you go a tenth of a micron, 10 to the minus 7 meters, 1/10 millionth of a meter, you begin to get you begin to see the double-stranded structure of DNA, which exists on 46 chromosomes that determine every characteristic of human beings. And as we go a factor of 10 further, we begin to see, of course, the molecular structure, the fundamental base pairs that was discovered to be the basis of DNA, the basic reproductive mechanism of humans. And when I was a young person, this structure had only just been discovered. It was only in a single human lifetime that we've understood the basic genetics and the basic chemistry, biochemistry, that underlies the nature of life itself. Here, of course, you can begin to see a carbon atom surrounded by its by the hydrogens that it can hold. A carbon atom can basically bind to 4 hydrogens, and the different ways carbon binds to hydrogen and oxygen, and in some cases nitrogen as well. You can begin to see the base pairs and the fundamental chemistry, the biochemistry of life. This is at a nanometer, a billionth of a meter. This is the scale, the outer scale of atoms. Of course, this is again an artist rendering. We can now with electron microscopes and other versions of electron-like microscopes, we can actually begin to visualize this scale in real life. But beyond this, we have to again do simulations, because the normal scales and the normal makeup of matter that we experience on human scales, when you get to scales of 1 angstrom, the size of an atom or less, matter becomes very different, because the rules of quantum mechanics can begin to take over. And the classical picture of an atom as just a heavy nucleus surrounded by an electron, of course, doesn't work. The electrons aren't billiard balls. They're quantum mechanical objects, in some sense spread out like a cloud around a very dense nucleus. And it's interesting, as we go in this scale at 1 angstrom, we've begun to permeate the cloud of outer electrons around a carbon atom. But it will take us several orders of magnitude inside before we get to even anywhere near the nucleus. As we've gone another factor of 10 smaller, a picometer, we now are in the region around the innermost electrons of the carbon atom. They don't even know what's happening, and the chemistry of carbon atoms is determined by their outermost electrons. At this point, basically, this region is almost insulated from all of the chemistry that determines the life and biochemistry that allows us to exist, to live, to breathe, to talk, and to think. Another factor of 10, and you can begin to make out the incredibly dense nucleus where almost all of the mass of the carbon atom resides, in protons and neutrons. Discovered again less than 150 years ago that atoms were really made of an incredibly dense nucleus surrounded by electrons. And here in this artist rendering, you can begin to see the makeup on a scale of a tenth of a picometer, 10 to the minus 13 meters, or now something we call a Fermi, named after the physicist Enrico Fermi, 100 Fermis. And a Fermi is more or less the scale of an individual object in the nucleus. We can begin to see the 6 neutrons and 6 protons in a carbon nucleus here. And as we get in closer, of course, in this artist rendering, you can begin to see these objects, which would not in real life look like this. They would be diffuse waves of particles. And if we try and look inside a proton, we now, again, only in the last 60 years or so, have we realized that protons and neutrons themselves are not fundamental particles. They're made of objects called quarks, which as far as we can tell are fundamental. They don't have colors. In order to distinguish the different kind of quarks, we give them weird names, weird colors, 3 different colors, many different names, and I'll describe them in a second. But in fact, actually, that was an image, that's the kind of high school chemistry image that you might have had of a proton in high school. But actually, inside of a proton, the laws of quantum mechanics and relativity are operating, and that's allowing virtual particles to pop in and out of existence on scales so quickly we can't see them, but we can simulate them. This is actually a mathematical calculation of what the space inside of a proton looks like as fields called color fields made of gluons pop in and out of existence. And it's these fields, not the quarks inside the protons, that are responsible for over 90% of the mass of the proton itself. An amazing discovery, and the nature of the strong force, these gluons propagate the strong force, is a discovery that was only awarded the Nobel Prize about exactly 20 years ago from the time we're talking now. This is our emerging understanding of fundamental structure. If we go a factor of 10 smaller, well, we're inside this scale of the proton and quarks, and we're beginning to probe the very limits of what we understand of matter. And in fact, we use the largest devices that essentially humans have almost ever made, the huge detectors, in this case at the Large Hadron Collider in Geneva, to try and probe matter on its smallest scales. And ultimately, we've discovered that the properties of all those quarks is determined by a field called the Higgs field, which was predicted to exist in the 1960s, and in 2012 was finally discovered. But you can see these mammoth machines that are needed to probe, basically huge microscopes, if you wish, to probe matter on its smaller scale. And finally, this is an image of, by the way, one of the events on July 4th, 2012 that was reported that demonstrated the existence of what's called the Higgs particle, which was one of the key elements of what's now called the standard model of particle physics, that demonstrated that our ideas about how matter was made up were more or less correct. And we have, on that scale, we're going down to about 10 to the minus 18 meters or so. We've gone from about 10 to the 26 meters to 10 to the minus 18 meters. That's the visible universe that we have explored. What's fascinating about that universe is over all of these scales, the visible universe, it turns out below this scale, of course, we have only theoretical ideas of what exists. And above that scale, we have only theoretical ideas of what exists, because physics is an empirical discipline. And while we've been able to predict things that have been correct often, almost anything goes on smaller scales than this or larger scales than this. And physicists like me, theoretical physicists, try to speculate not just what exists here to try and understand our origins and the largest structures in the universe, but to also guide experimentalists on things to look for. Of course, to get to this scale, to get to these incredibly small scales, takes a lot of money. If we could do it more cheaply, we would. But to build a large accelerator to probe the small scales we can do requires a lot of money, and the Large Hadron Collider costs about $10 billion. That used to seem like a lot of money. It's still a lot of money compared to some things, but a small amount compared to the money spent by various national governments today, like the United States. So you can ask yourself, is it worth $10 billion to understand the nature of the universe in which we live? Well, you can have that discussion with your friends. But over this entire scale of the visible universe, what's fascinating is there are only 4 forces that operate. And on the scale from the human scale out to the largest scale we can see, there's one force that operates that's important: gravity. But on the scale of humans down to atoms, the one force that determines essentially the entire nature of life, essentially everything we see and experience on a daily basis, the one force of electromagnetism dominates. Once you get to a scale smaller than the scale of atoms and the nuclei of atoms, it turns out the weak force that dominates, the force that can convert protons into neutrons and back and forth, and determine the dynamics of much of nuclear physics, and then on a scale even smaller than that, inside individual protons and neutrons, the force that dominates is called the strong force. There are four forces that completely describe the universe we can see. We would like to understand why there are four forces, why they have vastly different strengths. These are open questions at the forefront of physics, but it indicates how simple, in some sense, the universe is, and why, on scales larger than the Earth, you can ignore, in some sense, anything but gravity. And while on scales of humans and smaller, and gravity itself becomes irrelevant. To talk about that, I should describe the relative strengths of the forces. So we've got only those four forces known, and let me put this scale, this power of 10 scale, to the forces. So I've got a 1 here, and I've got a 10 to the 45 up there, a 1 with 45 zeros. If I put gravity, the strength of gravity is a 1, what's the next strongest force? It's the weak force. It's already 30 orders of magnitude stronger than gravity. That's why we can ignore gravity on human scales or atomic scales, because it's so insignificant that we can generally ignore gravitational effects. The weak force itself is weaker than the electromagnetic force on the scales that we exist on. The electromagnetic force is maybe about a factor of 1 billion or 10 billion times stronger, and the strong force is a factor of 100 times stronger than electromagnetism. So we have these strength of these forces varying by almost 45 orders of magnitude. Why is that the case? Again, an outstanding question at the forefront of modern physics. Well, that was the forces of nature and the scales of the universe. The next thing I want to talk about is the nature of matter. And matter looks complicated. If you look at the matter in this room, as I'm describing it now, it's many different forms. But what we've been able to discover is that at a fundamental level, matter reduces to very simple objects, quarks and these particles called leptons. Quarks are the fundamental components of protons and neutrons, 3 quarks on average in a proton and a neutron. And leptons is a weird name to describe the particles that orbit atoms. The simplest ones are electrons. There are other objects that don't orbit atoms called neutrinos, partners of electrons. They're released in nuclear reactions, like the nuclear reactions that power the sun. There are over 10 billion neutrinos going through me every square centimeter of my body every second, because neutrinos interact so weakly, only by the weak force, that they barely notice the Earth is even there. But it turns out there are electrons and neutrinos for protons and neutrons. It turns out there are 3 copies of the kind of particles that make up protons and neutrons, 2 heavier sets, and similarly for leptons there are 2 heavier sets. The heavy cousin of the electron is called a muon, and then a tau particle. And for the protons and neutrons, there are the quarks that make up protons and neutrons, primarily the up and down quarks. There's the charm and strange quark, and the bottom and top quark. But protons and neutrons combine with electrons to make everything we see, atoms. Everything, the diversity of everything we observe in the universe, atoms, is made up of just these fundamental particles as far as we can see. The visible matter, what's surprising is that the invisible matter, the stuff we can't see, is probably made of an elementary particle totally different than all of these. But every material that we can describe is just a simple combination of these particles. Now, matter exists in many different states, and one way to try and describe it is as a function of temperature. So this is 3 degrees above absolute zero. We're about 300 degrees above absolute zero in this room right now on what's called the Kelvin scale. And again, using powers of 10, I have 3 degrees, 300 degrees, 3,000 degrees, 30,000 degrees, etc. And at different temperatures, matter behaves differently. At 3 degrees above absolute zero, helium, the gas helium, liquefies. We have liquid helium, and we use it in our technology a lot to cool things down for superconducting experiments and other experiments. Water melts at about about 300 degrees, so a factor of 100 times the temperature which helium liquefies. Water melts, or if you go down, water liquefies. It goes from gas to liquid. At 3,000 degrees, metals melt. Now, what does it mean to melt? It means you're breaking apart the atomic bonds that hold things together rigidly. So melting takes place for even the most rigid materials at a few thousand degrees. You're breaking apart the atomic bonds. You're giving enough energy to materials to break apart their atomic bonds. In fact, at 3,000 degrees is when you are breaking apart the bonds that bind atoms themselves, like hydrogen, and that's why when the universe was warmer than 3,000 degrees, it was a plasma, and that's why we can't see past that cosmic microwave background. But if you go up, say, in an incandescent light, you're ionizing, you're actually tearing apart the electrons, not just from hydrogen, but in fact from even heavier elements. And a light bulb involved, an incandescent light bulb involved the ionization of breaking atoms apart, the electrons out of atoms. You have to go up to the center of the sun, about 10 million degrees, and even more than that, a factor of 1,000 times that, 30 billion degrees, before you're beginning to break apart not just the outer parts of atoms, but the nuclei of atoms. Stars, when they explode, the inner cores are heating up to a point when we can break apart the nuclei of atoms and put them together. And it's this process that produces the heaviest elements that we know of on Earth today. And then to look at even more energetic things, this is one of the first large accelerators, and then you begin to break apart protons and be able to see the structure of protons in quarks. When if you wish, you give as much energy, you give about a factor of 10,000 times more energy in onto a proton than you'd get in an exploding star. You break apart the protons themselves momentarily into their component quarks before they reassemble. And the Large Hadron Collider, of course, a factor of 100 times still, is the energy you need to liberate quarks. So you see 16 orders of magnitude, and in this case 14 orders of magnitude, then the energy associated with melting water is what we need to dump into a proton in order to explore matter at its smallest scales, which is why these machines cost so much money. But this is the kind of, as you think about the way matter changes its behavior as a function of temperature, what we're doing is we're breaking apart atomic bonds, then breaking apart atoms, then breaking apart nuclei, breaking apart protons, and ultimately looking at the object itself that we think gives mass to the quarks themselves that make up the protons. The last thing I want to talk about, so that's space and the structure. So we talked about space and matter. The last thing I want to talk about in this lecture is the nature of time. And I want to give a brief history of the universe here. Again, using the kind of scale that I hope you're beginning to get familiar with. Powers of 10 in size and powers of 10 in size in time. So this scale here, 10 to the 17 seconds, is about 10 to the 10th years. It's close to the age of the universe. The universe is about 13 billion years old, 1.3 times 10 to the 10th universe, maybe 14 billion years old. But that scale is the age of the universe. We go right back down to a time, 10 to the minus 42 years after the Big Bang, or 10 to the minus 35 seconds after the Big Bang. And then we look at the scale of the universe. Our universe has been expanding, and we can extrapolate backwards using gravity and looking at the scale of our universe and the objects that make up our universe, and we can try and consider a picture of how the universe scaled in time. So at the upper right-hand corner is the scale of the universe, of the visible universe, roughly 10 to the 28th centimeters. That's the largest scale I talked to you about in our earlier discussion. And we can try and extrapolate how if we go back in time, that scale of the universe would be. And you see that roughly, if we were to scale it directly, when the universe was 10 to the minus 35 seconds old, what is now the entire visible universe would have been a scale comparable to the scale, a little smaller than the scale of a man sleeping in the park of Chicago. So all of that mass and energy comprised in 100 billion galaxies, each containing 100 billion stars, was contained in an incredibly hot, dense region. It's hard to imagine such a thing could have existed. We can extrapolate our theories back. We can't, when we try and understand back here, we're talking about theoretical regimes that have not yet been directly probed, but we have actually directly probed the history of the universe back to relatively early times, as I want to show you. Now, on this power of 10 scale, you have to remember that each tick is a factor of 10 later than the tick before, and that means that the linear scale in which we normally think of time existing on is kind of strange here. So if I have A, B, and C, those three regions I've drawn there, A is when the galaxy formed, about 12 billion years ago. B is when the sun formed, and C is today, 13.7 billion years after the Big Bang. That's the history of the formation of our galaxy. All of that stuff is in the very upper right-hand corner. We can look and try and understand the formation of galaxies. We can look back with the James Webb Space Telescope now back to as early as a few 100 million years after the Big Bang. With our telescopes, we're going back to A or a little bit earlier. But we can go back earlier than that. We can try and understand when atoms first formed by looking at the cosmic microwave background. Because remember, that light comes to us at a time when protons first captured electrons, so matter was neutral and light could propagate. So if we go back and look at the cosmic microwave background, we're looking back at the universe at an age of roughly 300,000 years after the Big Bang, which we can probe directly. We can go back to earlier times. It turns out when the universe was roughly between a second and a minute, a few minutes old, the light elements formed. Before that, it was hot enough that even nuclei couldn't combine. We just had protons and neutrons. But as the universe cooled down to about 10 billion degrees, when the universe was roughly a second old to a few minutes old, then it turns out protons and neutrons combined to form helium. Most of the protons in the universe didn't form helium, and 70% of the visible mass of the universe at that time was in hydrogen. The rest was in helium, and a very little bit in lithium. And we can actually make predictions based on our nuclear physics measurements in laboratories of how much hydrogen, helium, and lithium should have formed in the early universe. When we go out and look at those, over 10 orders of magnitude, they agree with experiment and they agree with observation, telling us we understand the Big Bang at least directly and empirically back to when it was at least 1 second old. Before that, we don't have direct yet observations, but we know when the universe was roughly about 1/10,000,000th of a second old, it was hot enough that protons were being broken apart into quarks all the time. And if we can look for remnants of that proton-quark transition, then we'll be able to directly probe the universe back to when it was about 1/10,000,000th of a second old. The scale at which the Higgs particle began to give mass to quarks is a much earlier scale. This is the scale we try and probe directly at accelerators. We can't look back in the history of our universe to see it, but we can try and create the conditions of the early history of the universe in these incredibly hot, dense regions of the center of accelerators where particles are colliding. And we've been able to discover the Higgs, which means we can probe the kind of physics that governed our universe back to roughly almost a millionth of a second after the Big Bang. This is therefore all empirical. We can test these ideas by measuring things in the laboratory and then predicting what would happen in the universe. At a much earlier scale, a little bit longer than 10 to the minus 35 seconds after the Big Bang, which is a million billion of a second, unbelievably small scale, we think that it's possible that 3 of the 4 forces in nature became unified. That's called the grand unified transition. We've been trying to get direct evidence of this. We don't have it. We've been trying to get direct evidence of what caused the fact that the electroweak symmetry scale was that scale. Why are the 4 forces of nature have the different strengths they have? Why are there 4 of them? All of this depends on trying to understand physics here and even earlier at the earliest moments of the Big Bang. But this is theoretical speculation. If you're thinking about observation and experiment, we can probe the history of the universe now with our accelerators back to about a millionth of a second after the Big Bang, right up to the history of the universe today, 13.7 billion years after the Big Bang. But so this is the important stuff that took place in the history of the universe. But I want to talk about that last little bit in the history of the universe. So let me draw a line of 13.7 billion years and try and kind of consider a linear scale to give you a sense of how everything that's happened to us is really the last instance of this cosmic game of the evolution of the universe. So let me expand from a time of when the universe was 2 billion years old up to today of 13.7 billion years old. And you see, when it was 2 billion years old, that's around the time our galaxy formed, about 2 billion years into the Big Bang. And then our sun was only relatively recent, a newcomer in that scale. It was about 4.5 billion years ago is when our sun formed in this linear scale now. And now I want to expand even in that period, another linear scale. I want to go not from 2 billion years to 13.7 billion years. I want to go from 13.69 billion years, 13 billion years to 13.69 billion years into the Big Bang. And you can see, well, we're now less than 1 billion years ago. Certainly the first life forms, the first modern prokaryote kind of cells began to form, and things like the dinosaurs a few 100 million years ago. And then if you look at the very last bit here, where we expand from 13.69 billion years to 13.7 billion years, I have the cave people, but early hominids are here. And all of modern human history, all of recorded modern human history is contained within the width of that last line. The drama of everything that matters to humans is really, in a cosmic scale, just a blip, an instant in a cosmic history of the universe, which contains many, many important transitions that led to our existence today, and of course a future which could go perhaps infinitely long into the future. It gives you a sense of our cosmic insignificance. So that's history. All of history is that line, but for humans, but cosmic history is a much richer region here. And it's actually fascinating that if you think of the first second in the history of the universe, more events happened in the first second of the history of the universe than will happen in the entire future history of the universe, if you consider events like collisions of particles. So I've tried to give you a tour of the universe today that demonstrates what we know about the universe, how strange it is on large and small scales, and what we know and what we don't know about this remarkable universe of ours. And what I want to do in the next lecture is talk about the kind of tools we built up to try and understand that universe. Thanks. Hi, it's Lawrence again. As the Origins podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture.